I would like to introduce to our speaker today, Dimosthenis Kontogiorgos. I hope I got it right. So he's a postdoctoral researcher in the linguistics group at Potsdam University in Germany. He's also a PhD student right now, almost finishing at KTH Royal Institute of Technology. And he's been a visiting researcher scholar in many places, including Microsoft Research in Seattle, at the University of Southern California's Institute for Creative Technologies in LA. And Dimos is mostly interested in modeling how humans co-produce utterances in interactions with the principles of audience design and how conversational user interfaces and robots can actually simulate such adaptation strategies in interactions with humans. So, and that's exactly the topic of today's talk. So Dimos, whenever you're ready, the stage is yours.
Yeah, thanks a lot, Miguel, for the introduction, and welcome everyone. And I think we were talking before, but I didn't actually get the chance to thank you, organizers, for the invitation as well. So thank you as well. Just give me a second to share my screen. So can you see it?
Yes, perfect.
Okay, so yeah, so let's start. I'm going to talk about mutual understanding in situated interactions with conversational user interfaces, and this is also the title of my thesis, which is about all the theoretical, empirical, and computational aspects of mutual understanding with machines. And I wanted to say that I haven't, this is not a presentation for the defense, actually. So we have this peculiar system in Sweden where you have the concept of an opponent that is supposed to present the thesis for you. And my PhD defense is in the 11th of March, and I'll be happy to share the details for any of you if you want to join. So yeah, Miguel already mentioned that I'm a postdoctoral researcher in linguistics at Potsdam, and I'm about to finish my PhD at KTH. So first, I would like to start with a quote from a short film in the 60s. So you can say, of course, machines should work and people should think. And I like that quote, actually, even though it's quite old, it's not actually outdated. So that film is basically some kind of a commercial for IBM's Selectric Terminal. And what they thought at the time was that, okay, so they had a lot of paperwork and not a lot of time. So how could machines basically help into that problem? And this is how machines actually looked like at the time where they made that film. So this photo is actually 10 years later, but the Selectric Terminal actually you can see here in the front. So this basically was a vision that so it was expected that machines were expected to extend human capabilities. And why I like it is because it's very relevant today. Even though we have computer interfaces that can talk, and we typically use for information retrieval tasks. So the question is, how did people interact with computers in the past, right? So how do we do today? What has changed? And how we are going to interact with the future interfaces that we're going to design. So what is particularly important in this topic that I've been interested in is how we establish mutual understanding with machines through a variety of media over time. And so as this vision is relevant still today, a series of events have contributed to the development of talking machines. And in the next slides, so think about how did voice become a medium of communication for computers, and how did users establish understanding or recover from misunderstanding with machines. So what we know from the first reported synthesized human speech was that it was developed in the 30s at the Bell Telephone Laboratory. And here it is demonstrated at the New York World Fair. So basically, a human operator was controlling various parts of the machine, and you can see there was some sort of a keyboard that directly controlled acoustic components, such as the pitch or the spectrum, and that basically machine could produce words. So it was not a computer, but it kind of set the basis for synthesizing speech. And the same principles actually are still used today in the conversational interfaces. So it was also what you would call a wizard system. Only the difference is that the operator was actually visible. You of course must know the first programmable digital computer that was developed in the 40s, known as ENIAC. And this was still very different than interacting with computers using speech, but it kind of paved the way for general purpose computation. And here we can see, I think it's Merlin Metzler and Ruth Lichterman working on ENIAC. Then in the 50s, we had the Dartmouth workshop. By many is considered to be the birthplace of AI, co-organized by Claude Shannon, that you can see in the photo. And there they first discussed whether machines can think and if they can simulate thinking, but also how can they make use of language and also form abstractions. Then in the 60s, we actually start to get computation into synthesizing speech. And this was by Gunnar Fant from KTH. And he developed this device that was called OVE2 that made basically possible producing of unrestricted speech with vacuum tube electronics. And after this, we of course went to ELIZA. So this was around the same time, and it was probably the first chatbot that used language to interact with humans. And it simulated conversations with a psychotherapist using simple pattern matching mechanisms. Eventually, we get to what they at the time called smart terminals. And how people interacted at the time was that they used natural language commands. So basically, they used human metaphors to kind of navigate through a computer system. And even though most computers actually have still not made it to people's homes, it's about the time that actually HCI starts researching interfaces designed for users. And this is actually an interface I like. It's called Speak and Spell, and it was developed at the end of the 70s. And it's actually the first time that the computer and the speech synthesizer meet. And it was even considered at the time a kind of a milestone in digital signal processing. So this was used for it was some kind of an educational computer to teach kids how to spell words, and it used a built-in synthesizer to kind of voice the letters while being typed. Eventually, we also started seeing the first multimodal interfaces, and conversational interfaces, of course, as social robots are multimodal interfaces. And that began with the work from Media Lab, MIT Media Lab, that basically they envisioned that the office of the future will have interfaces that can recognize speech, but also gestures and eye gaze behaviors. Another multimodal interface eventually emerged also in the 90s, I think the late 90s, also from MIT, and it was called Kismet, as you can see here in the photo, and it's one of the first social robots that could recognize and respond to users' affective states. So we're getting very close. I know you think this is very old, but we're getting very close. So this is what they, of course, what you must know as the smartphone era. It was when basically Apple and Google started developing the first smartphones, which led to first the world's population carrying a digital computer in their pocket, and eventually to the development of personal assistants that were in the beginning used through mobile phones. And right after that, the first devices dedicated actually for personal assistants appeared that we now call smart speakers. So coming to the present, so this is in terms of research output in that area. So this is the number of publications you can see here from retrieved from Scopus, that they have these terms: conversational end user and interface, and it is from 1968 to 2020. And we can see that basically once the interfaces started being deployed in people's homes, a lot of research interest grew. And of course, some of the problems that we didn't know, they were not anticipated before deployment, and they're relevant to, for example, how people address interfaces, these interfaces. So, for example, to address conversational user interfaces, today we need some sort of a cue phrase, right? So you would say, "Hey Siri," or "Hey Alexa," which kind of resembles these push-to-talk interfaces. And that means that there are a lot of challenges remain open in how we, for instance, work with addressee detection and turn taking, but also language understanding and miscommunication. And regarding miscommunication, the brief history basically here was shown to kind of understand how users communicated with systems over time, and whether it is unplugging cables or punch cards, rewriting a natural language command, or rephrasing a spoken utterance. Who is it that is responsible for a failure detection when things go wrong? And for example, what strategies users employ to recover from system failures? So these are questions that have been, as far as I know, explored very little in HRI, and this makes the fields of psycholinguistics relevant in how people establish mutual understanding with machines. And this brings us to the common ground problem. I'm not sure if you're familiar with this, but it relates to one aspect of miscommunication. And I know that in robotics, it's not, I think typically people refer to the simple grounding problem, which is not exactly the same as the common ground problem, which views that basically language production is a collaborative activity. So this relates to a range of repair mechanisms that humans typically engage, and how they kind of accumulate common ground over time, and how do they also resolve miscommunication in that process. So, for example, when we interact with computers, there is this kind of limited single-turn transactional type of interactions, and problems appear, of course, because there's no user manual to know how to interact with a computer over speeds. So that means it's very hard to define what these interfaces can and cannot do without first establishing common ground. And this is why the problem is interesting. And according to Goffman, when people are physically co-present, they are very likely going to communicate with or without speech, which brings the question into focus of the concept of situation. And this basically situation refers to the sequences of events that happen in interaction when people are co-present, like in the photo. And situated interactions are driven by physical context, and they involved shared goals and motivations among people. Right. So, even though natural language is used for input and output, interacting with these interfaces kind of feels especially conversational interfaces, feels very similar to interacting with someone over the phone. And this is also due to the lack of situational awareness that we've seen before. And this is the promise that the human-robot interaction research has committed to over the past decades. So basically, they have envisioned machines that can not only interact with speech, but also share goals and intentions and engage in collaborative tasks, and kind of become more co-present conversational partners. And also how conversational interfaces look like is still an open research problem. And we also know that it affects how common ground is established. So, for example, you must know, I'm sure all of you must know here, the media equation that Reeves and Nash kind of defined through a series of studies. That, of course, computers are some kind of socio-technical objects, and that the more human metaphors are used, the more human likeness is ascribed. And that also means that the more expectations in behavior are also expected. And the use of human-like signals and behavior are also important in how mutual understanding is established. So throughout my PhD, I focused mainly on these questions and in also modeling how mutual understanding is established between humans, but also between humans and machines. And in some of the cases, I looked, for example, how this happens incrementally, and also how in the process miscommunication is resolved. And I also got interested in the notion of embodiment. And to approach this, I typically collected first human data with many sensors, and then built artificial agents that can imitate the same process. So, okay, so starting this line of research, and given, of course, that conversation is structured in such a way to also accommodate for miscommunication, we found that, of course, it is inevitable that when interacting with interfaces using speech, we will also encounter moments of miscommunication. And these moments are very critical because they can cause users to lose trust. So basically, unresolved failures, robot failures, can cause a lack of trust in the system. So failures in robotics can be explained in terms of lack of common ground, but also due to miscommunication. And in one of the studies we ran, we programmed robots to guide users through a cooking task. And then we also had them programmed to fail during that process. So we used a set of failures informed by previous studies in human-robot interactions that have been representing typical robot malfunctions. And they were all conversational, so either of task-oriented nature or of failures that violate social protocols of interaction. And all failures basically had the consequence of delaying users from their task. So here's an example of a failure. And in this particular failure, the robot simulates lack of user input.
I'm done. What is next? I'm done.
Sorry.
I'm done.
Okay, I'll play it again.
What is next? I'm done. I'm done. What is next? Oh, this is not working. I'm done.
Take 1 spoon of red cabbage and put it in the spring roll.
Right. So this is one type of failure, but we had several that I will also describe later. There was 2 types of interfaces that we used to kind of see mutual understanding and failures. And we kind of know that robot embodiment is typically positively affecting human-robot interactions, but we wanted to kind of see that the same happens when robots fail. So we used an Amazon Echo device that can only use speech by design. and a fair-height robot head that can also use gaze among the speech. And we also wanted to see if mutual understanding and recovery strategies differ when people are under time pressure. So basically, does the failure really matter, or is it non-affecting the interaction? So we used this timer, and half of the participants basically were under time pressure. And we expected that under time pressure, the same failures would have a higher basically severity on the task. So that means we had a mixed design study, and within factor was the embodiment, and the between factor was the severity of the failures. So basically with or without time pressure. And we asked people how likely they are to use this interface before and after they are exposed to failures. And we saw that while users' intention to use the human-like robot basically remains constant over time, the same doesn't happen with the smart speaker, but it actually decreases drastically after the interaction. And we also found differences on how message understanding is accumulated. So, for example, in low severity failures, people seem to understand better the human-like robot, while in high severity failures, it seems that they're actually better understanding the smart speaker. So this is when they're under time pressure. And this means that a human-like robot actually maybe distracts the user from the task when they are under time pressure, because perhaps they're displaying additional social behaviors. And using the behavioral data from humans, we also attempted to predict if a failure has occurred. And we also want to be able to use it in real time. So here, user behavior was represented in gaze and speech features, but also user actions. So a random forest classifier estimated correctly the failures with about 80% accuracy, and it was also better at detecting understanding than misunderstanding. So we also asked humans to estimate whether conversational failure has occurred, looking at short video segments of user behavior. So basically, they show exactly the same segments as the classification model, and from the perspective of the robot, like in the photo. So we wanted to compare how good basically our humans are at detecting exactly the same thing, detecting failures by only looking at user behavior. So looking at how the features were activated in the failure detection models, so we found differences across embodiment, even though the models actually worked equally well. So what we saw was that the gaze features were activated more when the human-like robot was present, while the opposite happened for the speech features. So that means that these subtle differences in features kind of show that the models are actually inherently different, even if they work the same with the same more or less efficiency. And that also means what does that tell us about behavior is that people speak more complex utterances with a smart speaker, but they take the easier way with a robot using their gaze to resolve failures, right? So it costs more effort to speak additional turns, therefore gaze in that sense is easier. And this is important for failure detection mechanisms that may need to consider interface design when actually building failure detection models. Right, so what we did then was we wanted to kind of generalize this. So we want to see if we can apply the same models in other data sets and of also task-oriented nature and also failure data sets. So we looked at HRI literature to look at the modalities that have been studied in robot failures. And a lot of HRI work has actually examined failures in robot perception. However, very few papers looked at behavioral signals. So, for example, we looked at literature that has embodied interfaces, like in the photos, even though there's a lot of literature from dialogue systems research that has approached the problem as well. And what we know so far is that humans respond with a variation in body movements and head motion, facial expressions, and acoustic features. So we use the instruction corpus on the left with the quicking task, and we also used what we call the negotiation dataset on the right, where participants basically needed to negotiate with a robot on a lunar survival task. So the instruction corpus is in this category of joint construction tasks, while the negotiation corpus is meant to create discussion. So we expected basically the grounding sequences to differ among the two datasets. So here's a failure example from the negotiation dataset, and here the robot basically keeps on asking for a repetition.
And what about sixth?
Can you repeat yourself? I didn't understand you.
My apologies. What did you rank sixth?
Can you repeat yourself? I didn't understand you.
Sure. What did you rank sixth?
Can you repeat yourself? I didn't understand you.
Let's see if this helps. Maybe you set my glasses. What did you rank sixth?
I ranked the nylon rope sixth.
The nylon rope.
Right, so you can notice how the user patiently continues to attempt to recover from the failure. So we started using the ASR input to determine the window of analysis. And we wanted to, once again, do real-time failure detection. So shown here, we use an IPU-based model. So that means that for every new user utterance that comes from the system, it attempts to evaluate if a failure has occurred in the interaction. So this means we have two states in the interaction, a no failure state and a failure state. And we started by looking into the extracted behavioral signals and analyze the features. And then we also trained classifiers to detect whether a robot has a failure has occurred. So we used automatically tracked behaviors to understand human signals, and also making sure that these signals can be extracted in real time. So for every user utterance, we present behavior in 3 feature encoders in visual, acoustic, and lexical features. And we use very standard tools such as OpenFace, OpenSmile, and BERT for text representations. We compare the reactions to failures with linear mixed effects models using the visual, acoustic, and lexical predictors. And we also run the models with the robot failures as a fixed factor and the participant as a random factor. And right, so data from this was from the linguistic inquiry. We saw that cognitive and affective processes such as tone, affect, and emotion, they kind of seem to be associated with how humans respond to failures. And that was also regardless of data sets, so that was kind of consistent. So what the numbers represent here is the percentage of words associated with each of these dimensions in its utterance. So at the same time, we saw that the number of words spoken in instructions is lower than in failure than, sorry, in no failure than in failure, while the opposite effect is observed in negotiation. And this could be some kind of a task-specific failure recovery strategy. When it comes to the visual features, we also found that that users consistently gazed at the robot. That was also regardless of dataset, and the numbers here basically show that numbers closer to 0, it's gazed towards the robot, so basically towards the camera. And right, so in both task domains, we also saw that facial action unit intensity was associated with the exaggerated articulation of speech, and I think that was also clear on the video. So when robots failed, users hyper-articulated their utterances. And finally, we also found differences in loudness. So in both datasets, users generally spoke louder in attempts to resolve failures. So this also appears to be a common strategy. And right, so we then once again attempted to automatically detect that the failure has occurred, and we started with the bidirectional LSTM on the temporal features, and we also used mean aggregated features per utterance with gradient boosted tree classifiers. So they were basically concatenated features in early fusion. And we see basically that even though there are some variations to the features on the failures, the responses are detectable. And in both the data sets, we also see that the significance of the lexical features. So the lexical features were the strongest indicator. At the same time, multimodal models achieved best performances, which is also expected since the tasks are situated and face-to-face. So the significance of nonverbal behaviors was also found. And finally, we saw in the post-hoc analysis, so what features are activated in the construction of the boosted trees. And we also saw that in the visual features, for example, were more informative in the instruction domain. So this is where we have this instruction type of embodied type of language and multimodal behavior. While, for instance, acoustic and lexical features perform the same in both data sets. So these findings basically show that nonverbal behaviors are actually quite consistent regardless of data set when it comes to response to failure. At the same time, lexical features could be more task dependent. So that means that robots perhaps may need to focus on nonverbal features that seem to generalize across situated tasks for detecting moments of miscommunication. And in attempts to kind of generalize these findings and the key takeaways, we found that loudness is significantly higher in utterances produced after failures. And we also saw that utterances in failures also indicate some kind of negative tone in their linguistic structure. And we also found similar gaze behavior across tasks. So basically, users always gazed at the robot when the failure has occurred. And finally, we also saw hyper articulation of speech as shown in the facial action unit intensity. So once again, the results here should be interpreted with caution. So there's of course limitations to how interactions are conducted, but also observed. And so basically failures, we can see that failures in human-computer communication can be viewed as deviation from expected behavior. And there's already theories on that, on human behavior, for example. And we saw that under time pressure, more human likeness may not be necessary. And in fact, sometimes even speech may not be necessary. So for example, it is more difficult to get information, especially large amount of information through speech. And it's easier to read. So I would like to finish with this credit to these 4 books that I enjoyed reading during my PhD, and would also recommend if you haven't read them. And I would like to thank you for listening and happy to take any questions.
Thank you so much, Dimos. And let me congratulate you on the session and on the talk. I think it was incredibly interesting, especially because I think that some of the lessons that you can take out of here can influence how we design social robots, right? Because I mean, these kinds of problems in miscommunications will always happen, faults will always happen. So maybe we can take out something out of there. And now we start the Q&A session. So if anyone has a question, please write them down in the chat, send to one of the co-hosts as a private message, or just raise your arm physically or using the appropriate button. And I think we already have a question by Filipe Correia. So Filipe Correia, if you want, you can ask, please.
Okay. Thank you. Hi, Dimos. Thank you for your talk. It was lovely. And the introduction and motivation, although a bit long, it was super interesting. Thank you for that. My question is, can you elaborate a little bit more based on all of your experience on the relation between how humans express upon failures and the embodiment and the anthropomorphic features of the robots? And I know you did some comparisons between a human-like robot and Alexa, for instance. But my question extends also a little bit to what's your opinion about voice and natural language? How do they affect the way humans express on failures?
Yeah, so voice is already, that's a good question. So voice, of course, is already anthropomorphic, right? So you expect that. So you wouldn't say that anthropomorphism is some kind of a binary.
Yeah, it's not.
So it's more of a continuous scale. So in that sense, I don't think we have the data to say that the more anthropomorphic, the more gaze, for instance, will be more gaze responses will be there. But right, but you could kind of expect that anthropomorphism is also changing the expectations of the user. So in a sense, the more anthropomorphic something looks like, or an interface looks like, the more human-like behavior will also be expected. So, and I think that's the problem with these interfaces that use only speech, like the Siri and Alexa, for example. That in a sense, you could say they're some kind of sophisticated Google search, right? So rather than typing something, you can voice that Google search. But at the same time, it cannot really respond to all the other human-like aspects of spoken communication. So I think it's better now than 5 years ago when they first came out, but typically they happen in one turn, and that's the problem of the anthropomorphic feature, that it kind of, in the beginning, you kind of think, okay, it can speak with me, so I can maybe engage in all these other behaviors. While the same is not the same doesn't happen, for instance, with a chatbot. Maybe we haven't done that type of a comparison, but that's what we expect.
I think Philip is giving a thumbs up. Thank you so much for your answer, Dimos. Next question by Rolf. Rolf, if you have a question, please go ahead.
Oh yeah, sorry. I think Sylvia was before me though, but I've just put my hand up. But I can go first. Thank you for the talk. Also, I have to say the introduction was super interesting, that collection of historic pictures in one place. It was really nice. I'm wondering about the nonverbal sort of failure detectors, because I think at one point you were comparing lexical, to nonverbal detectors, and you said they're more generalizable if we look at the nonverbal behavior, which makes sense. So I'm wondering how generalizable they are, do you think, across different tasks? Like if we had, just a very different chatbot or some chit-chat, open-ended chatbot or something, would they still work? These failure classifiers? And then also, have you experimented with handling the failures? And do you have any tips maybe on what would be also general purpose way? Like, would you go back to the beginning of the interaction, or would you give specific task-specific cues maybe? Yeah, thank you.
Right. Yeah, thanks, Ralph, for the question. That's a good point. I think maybe I mentioned it at the end, but actually the answer to the first question is we don't know. So all the interactions that I have also done through my PhD, but also most that I know of in HRI research, they're goal-oriented or kind of task-oriented. So very few actually go on what is called open world dialogue. So what does that mean is that you can imagine that you have a non-verbal signal. For example, if you told me now, can you pass, let's say that we have a dinner and you told me, can you pass me the salt? And I turn around and I pass you the salt, you kind of think, okay, that's expected, right? But if I keep on looking at you, you would think that there's something that I misunderstood, right? So my non-verbal signals basically are far more important than if we didn't do some kind of a task or goal-oriented actions. So actually, I don't know of any work in SRI at least that has done that. And the ones that I think it was in one of the slides, I think all of them are task-oriented. So I would say maybe some of the non-verbals actually are consistent, but probably I think we need to test it. So that's an open problem. And the second part of the question, can you remind me again? What did you?
Yeah, sorry. I mean, maybe it's the similar. Like, I'm wondering, how do you handle the failures?
Right. Yeah.
It's also in a task-oriented, task. Then it's obviously domain-specific what you would do if a failure occurs. But I'm wondering, have you done experiments with this?
Right. No. So actually, I haven't done any. I know I can see some of the people actually here. I think Liz Carter, maybe. Yeah, I think there are some people that have done also kind of recovery and what happens to how do you basically resolve it and or mitigate the failure. So that's a line of HRI work that has worked on different ways to kind of even explain why the robot failed or kind of mitigate. But I haven't done any of that work myself actually. So from our interactions that we have recorded, we typically have shown no indication of failure awareness. So the robot kind of continues the interactions as if nothing happened. I think there's a really good review paper from 2018. I think it's called Honig and Oren Gilad I think it's from Frontiers paper. They have a very extensive overview of failure recovery strategies, actually. So I would recommend that if you haven't read it.
Oh, thank you.
Thank you for the question, for the answer. I think Ruben also has a follow-up question. So Ruben, go ahead.
Yeah, thank you, Dimos, for the talk. It was really interesting. I was kind of wondering whether you could talk a bit about the different types of failures that you've investigated, whether or not you made any distinction between the different types. And also, I noticed that at least the examples that you gave were mostly related to whenever the robot didn't understand the user, but are there also any failures, or is there any research in the failures in the other way around? So when the user misunderstands the robot and that the robot then adjusts its conversation, for example?
Yeah, so we did a little bit of we had a little bit of a discussion on different types of failures in some of the papers as well. That I think they're also in the description of the talk. And so so there is I don't know of any work that did try to kind of look the other way around, so miscommunication from the user. So usually, so what we know is that some failures are more important than others. So for example, since we're still talking about task-oriented interactions, failures that cannot stop you from completing the task, they're very severe, right? So the user there actually needs the help of the computer to continue, while other failures they can pretend it didn't happen. If they think that they cannot be resolved, they can just ignore it. So the responses there are different, and I can't remember exactly the differences now, but in all the different types of failures that we had in these interactions, we at least saw that there's some of them are very clear, while others are not so clear. Now, what happens when the user misunderstands the robot? That's a good question. So how would the robot? Well, currently the robot wouldn't be able to even know this, right? So they would assume that everything is understood, which is a little bit naive. But I can't think of any work actually that does it. But I'm sure there is. I can't find any at the moment.
Yes, thank you.
Thank you for the question. Is there any other question? Sylvia, you had a question?
Yes, but I can ask in Slack if you don't have enough time, because it's also related with it's been asked before, and so the explanation. How would you like solve this miscommunication? But you said that you basically didn't work towards solution in that direction. So you kind of asked it my question too. But I will ask on chat Slack.
Okay. Yeah, I'll try to get on Slack as well on the channel, and happy to respond any questions there as well.
Yeah, that's a wonderful segue to remind people that we have a Slack channel where you can continue asking questions to Dimos or interact with him, ask him questions. And the link will be in the chat. We have time for one final question, if anyone wants to ask. If not, we go to our final part of the session. Then I would like once again to thank Dimos for the presentation and for the Q&A. I think it's
Thanks
super
as well.
interesting. And I would just like to take 2 more seconds of your time just to show and talk about the next speaker of Talking Robotics, which as usual will be in 2 weeks from now, so on Wednesdays. And it will be Samantha Reek from Carnegie Mellon University, and she'll be talking about characterizing agent identities as mediators among individuals, embodiments, and services. So that talk will be in 2 weeks. And if you want to get up latest news, please follow us on Twitter or subscribe to our mailing list. Having said that, I would like once again to thank our sponsors, Animatas and Semio, without whom this project would not be possible. And having said that, well, I wish you a pleasant week and see you in 2 weeks.
Thanks a lot.